I want to continue today's lesson on where I left off last Friday on motion along a line. This was a very abbreviated lesson on motion, and today in class we talked about the position of a particular particle at various points in time and whether the particle was actually slowing down or speeding up or turning around at particular points in time. So what I'm going to do is I'm going to take this function that I gave you last Friday, this cubic, and we're going to talk about the position of the particle, and we're going to describe the movement of this particle along the x-axis. So that's today's lesson. I think I'll just draw a line down here and say, let's describe the movement of this particle along the x-axis. The movement and the position of the particle on the x-axis at various points in time. So we'll look at this. We'll look at this function, and we'll figure out where this particle starts off. Where's the initial value of this function? In other words, we're trying to find where it starts, which is at x of 0. So let's add this. X of 0 means the position at time is equal to 0, and that's also called an initial position. And in this case, all you have to do is plug in t equals 0 and get 0 minus 0 plus 0 minus 5. So x of 0 is equal to negative 5. So that's where we're going to start out. And then we're going to describe the movement as it starts out. So v of 0 means the initial movement. And that just means, is it moving to the right or to the left? And if we took this velocity function and plugged in a t equals 0, we'd get a positive 22. So the initial movement, v of 0, is equal to 22. It just means it's moving to the right initially. And we'll set this all up on an x-axis so we can summarize this at the end. And then if we want to know where does the particle stop and turn around, so in other words, it starts at negative 5, it goes to the right, where does it stop and turn around? Well, it stops and turns around where the velocity is equal to 0. And we already figured out where v of t is equal to 0 because we factored that and we put it on this sign table, and we figured out it moved to the right, and then it moved to the left, and then it moved to the right. Well, all that means is that the particle stops and turns around at 1 second and 3 2/3 seconds. So that's at t is equal to 1 and t is equal to 11 over 3. And so now what we're going to do is find out where does it stop and turn around, because we didn't calculate those x values. Where is this? Or where does this happen? So if you're talking about where, you're talking about a position function. So where means position. And what we have to do is we have to calculate x of 1 and x of 11 thirds. Well, if x of 1 is pretty easy when you put in x equals 1 into this cubic and you calculate those values. You can just get 2 minus 14 plus 22 minus 5, and you could calculate that to be x of 1 is equal to positive 5, I believe. But x of 11 thirds is a little bit trickier because you're going to have to cube 11 thirds and square 11 thirds. So I put that in my calculator to calculate that out, which is fine. If I ever give you a problem like that, I would allow you to use a calculator so you wouldn't have to do all that really nasty arithmetic. So x of 11 thirds is approximately equal to negative 14. Not exactly, but it's pretty close to negative 11 or negative 14. So we'll use those values along the x-axis. And then sometimes we're asked, where does this particle cross the origin or pass by the origin? And we didn't talk about that in class today. Where does the particle pass the origin? Well, the origin is where x is equal to 0, or sometimes, or not where, but at what time? Sorry, at what time does the particle pass by the origin? So in other words, at what time does the particle reach x equals 0? So what we would have to do is set the original x of t equal to 0. X of t is equal to 0, and then we'd have to solve for t. Well, that's not an easy task for a cubic function like this that we can't factor, so we would have to use a calculator to calculate the zeros on that. And I'll show you what that means. So I'll just say use a calculator on a tricky function like that. All right, I've run out of room on that page, so let's go into the next page. And let's put everything together here on the x-axis. So here we go, we've got particle movement. Maybe I'll even draw a straight line. Oops, haha. So here's my straight line, which represents the x-axis. And this x-axis means the x value at any time that's equal to t. So if you remember, when time is equal to 0, we had the x value being equal to negative 5, but then we also had an x value being equal to negative 14. It looks like that's the leftmost spot. So we'll start out over here on negative 14. All right, we went all the way up to the initial position was at x equals negative 5. And then we also calculated a point where it turns around, which is x equals 5. Let's see, the distance between this would be 9, and the distance between negative 5 and 5 would be 10. So it's about equal distance between all of these points. So here is the initial position of the particle, and that's at t is equal to 0. Well, the particle starts moving to the right. We calculated that. And it keeps on moving to the right until it gets to t equals 1, because we found that x of 1 is equal to 5. And then it turns around. So it turns around here, so we'll just put a little particle up here, and it turns around and it moves to the left after that. So initial, it moves that way, and then it comes back and it moves that way. Well, then the particle moves to the left all the way until you get t equals almost around negative 14, not exactly, but pretty close. And so at this point in time, this t value was equal to 11/3. And then the particle turns around and moves back to the right, and then it just moves to the right forever and ever. And so this gives the various positions of the particle along the x-axis. Now, where does it pass by the origin? Well, the origin is right here, halfway between negative 5 and 5. So here's the origin right here. And it passes by the origin sometime between 0 and 1 second, somewhere between 1 second and 3 2/3 seconds, and then it passes by again somewhere beyond the 11/3 seconds. So we can calculate that, but we'd have to use a graphing calculator. So I've already put this into my graphing calculator, the original function. And if you press the graph button, you would see that this is the position of the particle. It starts out, and you can see on the table of values, it starts out at negative 5. After 1 second, it's at position 5. So this just tells the position of the particle, various points in time. And somewhere between 3 and 4 seconds, it reaches the negative, almost negative 14, and then it turns around and comes back and becomes positive. So I did a second calc 0, and I think everybody knows how to do second calc 0 on their calculator. But I calculated it passes by the origin. At time is equal to 0.273. So on its way by, this point right here is t equals 0.273. And then I did a second calc, that would be the first 0. That would be that calculation. Then I calculated that 0, and then I calculated that 0. So there are 3 places that it passes by the origin. And those x values would be corresponding to the t values. So the second time it passes by the origin, at this point right here, this t value was equal to 1.898. And then it kept going, and then it turned around and came back, and 4.830 was the last time that it went by the origin. So sometimes those kinds of questions are asked. When did it pass by the origin? So you've got 3 times, 3 points in time, and those are the 3 t values that correspond to this. Now, if you had an easier function, if you had a function that you could factor and solve for x, then I wouldn't allow you to use a calculator to calculate the zeros. You just have to factor that and solve it for x. So the last thing that I wanted to talk about was whether the particle is speeding up or slowing down. Now, speeding up means that both the acceleration and the velocity are positive. So what I'm adding to this is the graph that you had from last Friday, and I'm hoping that you put them on one above the other, and you kind of corresponded the t values here. And what I did was I added a t equals 1 here because this corresponds to the velocity change, or the velocity reaching 0. And this corresponds to the velocity reaching 0 here at 11/3. These are critical values. And I'm putting one on top of the other because if you do that, you can see that right here in this position, or in this part of your sign tables, you have a velocity that's positive, but you have an acceleration that's negative. So because you have different signs here, the particle is actually slowing down up until it gets to 1 second. So the particle slows here. But then when you reach the time equals 1, that's this section of the graph, all the way up until time equals 2 1/3 seconds, you have both the velocity and the acceleration being negative. So this part of the graph, the particle is speeding up because velocity and acceleration both have the same signs. Well, then you move over past 2 1/3 seconds, and you get between 2 1/3 seconds and 11/3 seconds in this area right here. You have a velocity that's negative, but you have an acceleration that's positive. So in this section, between 7/3 and 11/3, you have the particle that's slowing down again, which makes sense because it has to slow down before it turns around and goes in the other direction. And then the last point in time, which is 3 2/3, all the way until the end of time, you have both the velocity and the acceleration with the same time, so this particle is speeding up again. So when it starts moving to the right, it's slowing down, turns around, speeds up, and then it slows down, turns around, and then it speeds up again. The next thing I want to talk about is the corresponding concepts between function and motion. And these concepts are calculus concepts between terms to describe functions. Oops, if I can write. And linear motion. So we've been working, all the calculus that we've been doing so far has been on functions. Like I've given you an f of x and we found a derivative, we've set it equal to 0. Maybe we found a second derivative, set it equal to 0. And we talk about maxes and mins and inflection points. But that also has a correspondence to linear motion where the particle is moving to the right or to the left, or it's stopping and turning around, or maybe it's speeding up or slowing down, or the acceleration is positive or negative. So I'm just going to put a chart together that shows the correspondence between those two ideas. So we have the idea of a function. And we have an idea of linear motion. And linear motion means it's just moving to the right or left, or an object is moving up and down vertically. So this is either vertical or horizontal motion. So the function, one of the terms that we use to describe a function is the value of the function at x. And that is actually equal to f of x. So that's when we're talking about functions. But when we're talking about linear motion, this is the same concept as a position at time t. T is a variable here, x is the variable here. So oftentimes we either use x of t if we're talking about motion along the x-axis, or sometimes the position function is called the letter s. It looks like a 5, but this is the letter s of t. So t is the independent variable. Okay. When we're talking about function notation, we do f prime of x, which is the first derivative, which gives us a slope, or it gives a local min or max. But when you're talking about linear motion, that means velocity. The first derivative of the position function, v of t, is equal to x prime of t, or if you're using the notation s of t, it would be s prime of t. So position velocity means the original function or the first derivative, and then we have a second derivative, f double prime of x, and that talks about concavity. First derivative is the slope, second derivative is the concavity if you're talking about a function. But the second derivative in linear motion is acceleration. Acceleration is a of t, which equals v prime of t, the first derivative of the velocity function, which equals the second derivative of the position function, or s double prime of t. When you're talking about functions, sometimes we're talking about functions that increase. An increasing function just means the graph is going up, or the y values are increasing. But for linear motion, an increasing function means that the particle is moving, it's either a particle or an object, moves to the right or up, if we're talking about vertical motion, horizontal motion, vertical motion. If the function is decreasing, increasing means the function goes up, decreasing just means the function goes down. And in linear motion, it means the function is moving to the left or down. Horizontal or vertical. Sometimes we talk about an absolute maximum. And you can calculate absolute maximums on the function with derivatives, and we've done that enough for you to know what that is. But if you're talking about an absolute maximum in linear motion, it means that it is the farthest to the right on the x-axis, or the farthest up if you're talking about vertical motion. So sometimes a question would say, where is the particle the farthest to the right? Well, what you have to think of is that means absolute maximum. And the same thing with the absolute minimum. That means the farthest to the left or down. Okay? When f prime of x, the first derivative is equal to 0, that means the particle is at rest. Sometimes you call it at rest, or what I've said in class, it turns around. When f prime of x changes signs, that means the object changes direction, or object turns around. Oh, this turns around, this is possibly. Usually it does. But sometimes f prime of x equals 0. It moves from a positive to a positive, or a negative to negative. So sometimes it just stops for a moment and continues in the same direction. But if f prime of x changes signs, it means the velocity changes signs, and that for sure means the object turns around or changes direction. It means it goes from up to down, or down to up, or left to right, and right to left. Okay, so if y prime is positive and the second derivative is positive, all right, so the first and second derivative is positive, or the first derivative is negative, you know what, I should say positive, or the first derivative is negative and the second derivative is negative, what happens there is your speed is increasing. Or in other words, the particle is speeding up. But if you have y prime is negative and y double prime is positive, or the first derivative is positive and the second derivative is negative. In other words, if they have opposite signs, if first and second derivative have opposite signs, that means the speed is decreasing, or the particle is slowing down. All right, I think I've talked enough. I'm starting to get laryngitis here. So that's about it, and hopefully that wrapped up everything that we were talking about today in class. Have a good night. See you tomorrow.